Hi, everyone. Welcome back. I am pretty sure you're a geek because you are watching a video on the topic of surrogate optimization. And if you really like optimization problems, especially using Python, you should watch the last few videos in this series where I did spend a little bit of time talking about various metaheuristic algorithms, including particle swarm optimization, simulated annealing, and so on. Genetic algorithms, of course. And in this video, I'm going to quickly provide a overview of surrogate optimization. And in fact, I didn't even intend to record this video, but I saw someone asked about this algorithm in the comments. So I thought, why not just cover one more optimization approach? Now, if you want your topic to be addressed, and if I have the skills in that specific topic, I am more than willing to record videos on that. But please leave your comments down below and also find the subscribe button underneath and hit the subscribe button so you get notified whenever new videos show up. And of course, the thanks button is right next to it if you're feeling extra generous. Okay, without any further delay, let's jump into the topic of surrogate optimization. And what does surrogate term mean to you? That means someone else or something else is taking the load or burden of what you're trying to do, right? I mean, you're kind of using a surrogate to get the job done. So in this case, surrogate refers to exactly the same thing. We are going to use a surrogate algorithm, not the actual algorithm, to optimize that specific objective function. Now, let me jump into it. I don't want to just talk and not show anything. We are going to the plan is go through a few slides. I know slides are boring, so you can just skip through it all the way to the coding part if you really don't care about the inner workings of this. And the goal is to go through those and then jump into Python code and try to understand exactly what the surrogate optimization is. And then at the end of it, I'm going to show you how you can just use some off-the-shelf library to get the job done. But it's very important for you to understand exactly what happens when you're using this algorithm. That's the whole point of this specific video. So I hope you're still listening. So let's go ahead and jump in. So first of all, what is surrogate optimization? Again, it is a method to optimize extensive objective functions by building a cheaper surrogate model. So when I say optimize expensive objective functions, basically means normally it's not easy to go through these objective functions, plug in your values, and then get this. So it's a bit complex objective function. So you can use the objective function and use particle swarm or any of the metaheuristic approaches. By the way, this is not a metaheuristic approach. In a way, heuristic is you're kind of doing some trial and error. Here, there is a probability-based approach. Again, you'll learn about it hopefully in the next 15, 20 minutes or so. So you kind of, instead of using your expensive objective function, you look for a cheaper surrogate model that is a bit faster to actually optimize. And that surrogate model obviously represents your objective model that you're trying to optimize. That's it. So that's the goal, right? Efficiently find a global optimum of your objective function with fewer evaluations. So you're not wasting your time trying to find this optimal. Now, what applications? Primarily engineering design, but you can use it for hyperparameter tuning and financial applications. There are many other applications, just like any other optimization. Excuse me, my throat is a bit scratchy from all the allergies. So what does this basically mean? Like this line from the previous slide. Optimize expensive objective functions by building a cheaper surrogate model. Well, I kind of mentioned it, but basically you're approximating the behavior of your so-called expensive objective function using a easy to evaluate or cheaper to evaluate, meaning it's more efficient, faster, and all that stuff, using that type of model. Where do you get this model? What do you know? How do you know what this model is? Well, there is a lot of text here, but the choice of the surrogate model, which model do you want to pick, depends on, of course, your objective function. For example, Gaussian process regression is something that is most commonly used because it's used for smooth functions, and it's a data-driven approach. Again, I'll let you read what else is on the screen, but this is what it comes down to. Now, of course, if you have polynomial functions, there is something called polynomial regression, and you can use radial basis function for nonlinear functions, and you can even use neural networks if you want as a surrogate model. you can do in-depth research on what this just topic itself, right? And support vector regression for high dimensional data. And you can use metaheuristic algorithms, optimization algorithms. Remember, that's what we have been covering the last few videos, particle swarm and all those, to optimize the parameters of this surrogate model. If none of this makes sense to you, hopefully it starts to make sense once we jump into the Python code and start to execute a few lines at a time. Now, key components of this optimization. What do we have? The first thing is Gaussian process model. This is the most common surrogate optimization. So it provides a probabilistic prediction. So what did we discuss? So the first one right there, Gaussian process regression, right? So that's what I'm referring to here, Gaussian process model. It provides probabilistic predictions with mean and uncertainty. What does that mean? When you apply this model onto your function, it doesn't just give you a value, it gives you the value, the mean, and also the uncertainty associated with that value. So obviously the term probabilistic prediction applies here. Why are we using this? To help estimate the objective function at unobservable points. Again, we'll jump into the code to slowly understand this. The second component here is something called acquisition function. It helps us in selecting the new points to evaluate. I know at this point it's all probably very abstract to many of you, but the more you hear about these terms, the more the kind of you tend to digest them. So these acquisition functions are designed to balance both the exploration and the exploitation. So again, what does exploration mean? Uncertain areas, and exploitation is, okay, you already know there are some good areas, and it's going to exploit those. It's going to use those good areas. And excuse me, the most commonly used acquisition functions are expected improvement. I dare you to go read about this because you'll see a lot of functions, and I'll give you a link and you can read more about it, but I'll try to simplify it as much as I can when we're discussing this in the code. So expected improvement or probability of improvement, like these are the two approaches. In my example, I'm going to show you expected improvement. And the acquisition functions, again, the purpose is to select the next point to evaluate, because initially you initiate with some random values. But then once you get the random values and you kind of fit the surrogate model, meaning the surrogate model understands what your actual model is doing in a way by looking at a few data points, then you need to create next data points, right? How do you create next data points? There needs to be some sort of a fitness, right? So this is where the acquisition function fits in. So the components of acquisition function is like predicted mean and standard deviation, the improvement, and expected improvement. And expected improvement I already mentioned in the previous slide. And this is a simple 4 or 5 line code that kind of encapsulates this entire expected improvement here. So what are we doing here? So basically by applying our GP function, again, what is that GP function? So here, Gaussian process model, right? So by applying our Gaussian process model, if you look at the first line in that function, mu sigma, if you apply that, because it's probabilistic model, right? And you're applying it, that means it gives you the mean and sigma. Now you take that mean value and compare to the minimum value that you have in your range that you define in the bounds, and that is your, let's call this improvement IMP. And if this improvement again is, let's get to that when we get to code, but then the next step is to normalize this improvement by dividing with the uncertainty with the sigma value, and then the expected improvement is nothing but your improvement multiplied by your, did I explain what CDF and PDF is? Again, I'll save this for the code because I kind of annotated the code very well so you guys understand it, but you see what the structure is right here. It's very simple. Now, optimization process itself, how do you do that? You initialize, I just explained that, you initialize this points and fit a GP model. You just fit that. At this point, excuse me, the GP model understands your inputs and outputs, and you're fitting it to this. Think of this as a machine learning model where you have certain inputs and certain outputs, and you're fitting this machine learning model. And in this case, it's a regression model because you're predicting a continuous variable, and that's what you're fitting right there. And then from that point on, you can use the GP model for optimization purposes, and that's basically what's going on here. So the candidate selection, so you generate multiple starting points. It sounds very similar to genetic algorithm, right? You generate the candidate algorithms, and then you minimize the acquisition function. How do you do that? You need an algorithm to minimize it. And one example algorithm is LBFGS-B. And what does that stand for? You can read that: Broyden, Fletcher, Goldfarb, Shano algorithm, apparently, which is suitable for optimization problems where you have specific bounds, where you know the answer lies between -10 and 10, for example. So in those cases, this algorithm can be very good to find the minimum. And then you compute the objective function, and you update the model, add the new data to the data set, and refit the model. I'll summarize this in the next couple of slides, but this is please go with the flow for now. And of course, after all the iterations are completed, you have your final solution, hopefully. Here is a snippet of code where we are showing you the loop right here, right? So you generate the candidate elements first, and then you have this list, and then you find the minimum in this list, and that is your next point. And your next point, you plug that thing into your objective function, which gives you the next value. And then you initial points, initial values, and you kind of fit this GP function with those two. And basically, every iteration, you're updating this. So here, I should have animated this slide, but I'll leave this on the screen if you want to pause and digest this. All the slides that I mentioned about until now, this is basically a summary of it, right? So you begin with it. I apologize for the colors. I suck at finding the best colors that fit on the slides. I just clicked on some random colors. But anyway, we initialize the surrogate model. How do you initialize the surrogate model? Surrogate model in our case is our GP model, right? So you choose the model type. Of course, we did that. You specify any hyperparameters that are required to tune or specified in your model. So we'll do that and select the initial sample points. These can be some random points that you generate and fit the surrogate model to initial data. What does that mean? You have like some initial random inputs within the bounds. You plug that into your objective model. It gives you some outputs. You take these inputs and outputs, and you train the regression model, which is our GP model or our surrogate model in this case. So you're fitting the surrogate model. Now the surrogate model is ready to be used later on. How do you do that? So select the next point to evaluate. So use the acquisition function. In our case, we're going to use expected improvement model, and we are going to minimize the acquisition function to find the optimal point. And then we're going to evaluate the objective function at that selected point. The next step is update the surrogate model. So now we update the model, in our case again, the GP model with this new data, add the new data point, refit the surrogate model, and until how long do you want to do that? Well, until the maximum iterations are reached, let's say 30 iterations, 50 iterations, how many ever. In some cases, you can actually put some convergence criteria, like, hey, if the function value, doesn't change by this much, then go ahead and stop. So you can put some convergence criteria, and of course, the output is going to be your global optimum or the best point and the cost function. So again, maximum iterations reached, or if you get the best cost function, or if the cost function is not changing within certain limits, then you can actually stop this iteration. So this is, in a way, the summary of our surrogate optimization. So let's go ahead and jump into the code, and hopefully things make more tangible when you look at the code. Hopefully you'll get that aha moment then if you haven't already reached it there. Okay, so let's jump into our Colab and continue the discussion. I have zoomed in quite enough. Hopefully you should be able to read it, and hopefully you're not watching this on your just tiny phone, which is fine, but when you're actually trying to get your hands dirty, please watch this on a real large monitor so you can see and read things. Okay, so where are we? All the stuff that I just talked about, I just added up here, but let's go ahead and look at the first part. This part is exactly the same as the last few videos where we just imported some libraries and we defined our objective function. In our case, the objective function is nothing but x minus 4 squared plus y minus 5 squared plus z plus 6 squared. You should know what the solution for this problem is. It's nothing but x equals to 4, y equals to 5, and z equals to minus 6, right? So I'm using this simple function so we know what the answer is. And I'm defining the bounds to be between minus 10 to 10. Yeah, x is between minus 10 to 10, y is minus 10 to 10, z is minus 10 to 10, right? I'm just leaving this quite open, so let's go ahead and run this. And a couple of things I should point out while this is running is I'm importing something called normalization from scipy.stats, and from scikit-learn Gaussian process, I'm importing Gaussian process regressor. This is the GP model I'm talking about. This is the surrogate model that we're going to use. And also from the kernels, I'm importing something called mattern. I added some notes about it in case you're not aware of what that is. And of course, optimize, minimize is what we are going to use to find the minimum of a function. So hopefully this block makes sense. Now, what is the next step? It's randomly sampling a few initial points, right? So now we have like the initial space is between minus 10 to 10. So let's get 10 points, right? Or 5 points in this case. Number of initial points 5. So let's randomly sample them. And how are we sampling? We are doing random.uniform. And low bounds is our low bound. You can tell, see here, high bound is 10, so minus 10 to 10. And get 5 random points. And obviously the dimension is 3. We have x, y, z in our case. And yeah, so let's go ahead and do that. And I'm going to print the initial points so you can see what they are. So they must lie between minus 10 to 10. So here the initial point is minus 4.6, whatever, minus 5.8, 4 point. And then these are all the initial points. If you plug this initial points into our objective function, what value do you get? You get a value of 300. Again, this is just the cost function value. 198, 136, 401, 364. If these are the options that are given to me, I would pick the 136 one, which is 1, 2, 3, right? So probably the third one here as the solution, but obviously that's not the right solution. Our right solution is 4, 5, what is it? 4, 5, and minus 6. So we need to work. We need to earn our lunch here. We need to work to get the right solution. Okay, so far what did we do? Initialize the points, and we looked at the initial values. So we know what the initial points are, what the initial values are for our objective function. But we don't want to use our objective function throughout the process because that's the whole point. Our objective function is expensive computationally, and it's not efficient. So let's actually go and find a surrogate function that kind of understands what we are trying to achieve with our objective function. So how do we do that? So our surrogate function is the GP, Gaussian Processing Regressor, is the surrogate function. How does it understand like our actual function, our actual objective function? It doesn't until we train it on inputs and outputs, which we just got from the previous exercise, right? Inputs, and these are the outputs. I'm going to plug those as input into my Gaussian processor. Again, this is where I defined my kernel for the Gaussian processor as mattern with a new value of 2.5. I think I included this. Yeah, the mattern kernel, it's a popular choice or a kernel for the Gaussian process. It's more flexible than other alternative like radial basis because there is an additional parameter that you can kind of fine tune it. This new parameter, I think if it's a value of 0.5, I did not include that, but it doesn't matter. If it's 1.5 or 2.5, yeah, it will lead to smoother functions. So I put a value of 2.5. You can put something else if you want and experiment with. But this is a kernel that goes in as an input to the Gaussian process regressor, and then and then the other parameters you can just go ahead and experiment with those. So we initiated this regressor Again, it's a machine. Think of this as a machine learning algorithm where you're training it on your values. What values? Your input values are the initial points, and your expected output is initial values, right? So we're training that on this. So let's go ahead and do it. Okay, so far, what did we do? We trained our surrogate model on our inputs and outputs. Now comes the acquisition function. And again, as I mentioned earlier, it guides the search process for the next point to evaluate. What is the next point that we want to evaluate? And we have to do this in an iterative way. But first, let's define the function for acquisition function, and then use that iteratively as part of a for loop later on while we go through the evaluation. Okay, again, a lot of text if you want to read on your own time. Again, please look for the link to the code down below in the description. So here is the primary function. Again, I think I showed this to you as part of the PowerPoint slide, but what are we doing here? We are using our GP function, which is nothing but our model, I should say, our Gaussian process regressor. We just trained it. And we are using the trained model to predict on these values. That's it. And when you do that, when you predict using Gaussian function, because it is probabilistic, it's going to give you two outputs. One is going to be the mean value. The other one is going to be the sigma, the uncertainty associated with that. You need those two to actually do your expected improvement. Yeah. So I put this in a with NP error state divide because sometimes you may encounter zero values. And in case you have that, all this is saying is, hey, go ahead and throw me a warning sign and don't just stop. So that's what this is. And my improvement is basically y min minus mu. And if this improvement value is positive, meaning mu or mean here is smaller than y min, that means it indicates that x value, right now, the one that we're using here, the input, has the potential to improve upon the best value. So that's what we are using here. And z is basically nothing but your improvement, but normalized by the uncertainty value. And then we are going to plug those into our expected improvement. Again, you need two things here, CDF and PDF. Did I define what CDF and PDF is? I should have if I did not. I apologize. Oh, sorry. Here. This norm.cdf is the cumulative distribution function of this normal distribution, standard normal distribution. And PDF, as you can probably imagine, is the probability density function of the standard normal deviation. Again, you can read this paper, this blog, I guess, which did a pretty good job explaining it, but there is a lot of math involved. But it comes down to this. Basically, it comes down to this. Your improvement times CDF, norm CDF, plus sigma times norm PDF. That's it. And then we are basically saying if sigma is 0, that means the prediction is 100% certain. Then the expected improvement is set to 0, and you're returning the expected improvement. That's it. Okay. Now comes the actual loop where we are going through these different data points. So do this for 50 iterations. Do what? Go ahead and look at the candidates. The candidates we are going to generate randomly using uniform, and our lower bounds is -10 in our example, upper bound is 10, and go ahead and create 10 random candidates of size 3 because we have X, Y, and Z in our case, and then optimization happens. Again, I put a lot of text. So what's happening here is optimization of the acquisition function for each of these points, 10 points that we just generated, and it stores the optimization into this list. Okay, and to find the minimum, we are using this LBFGS-B, which refers to this, that name, and it's apparently good for bound problems. I think that's it. So from this list, we are going to find the minimum right there, and that minimum is going to be the defining the next point, the x for the next point, and that next point is plugged into the objective function. You get the next value when you plug that into the objective function. And that's it. So you're, again, fitting this with the next points and the next values. Basically, and getting this updated fit of your surrogate function. And you do this in a loop for how many ever points. And of course, you're going to print the results in terms of what the best, what the points are, what the values are, and what the objective value, what the cost function is. This is it. And it's kind of simple and straightforward, but you may have to run this line by line to again understand exactly how the outputs look like from each of these lines. So let's go ahead and run this. And let's scroll down. It's by the time I'm scrolling down, it's actually done. It started off with a best cost of 77. It went down to 17. Obviously, it's trying to minimize the cost function, right? So that's what optimization is. Obviously, it was done like right here. But let's see how good the values are. Okay, so the best position is 4 point something. Again, we are not just dealing with integers, we're dealing with floating point. That's why, but if you round this off, the answer is 4, 5, and -6. That's what we're looking for, right? So this is how surrogate optimization works. Not sure if you guys understood what I was talking about, but watch this 2-3 times and run this line by line to see if it makes sense. Now, if you don't want to do that, you're lazy. You just want to use off-the-shelf model. There are many libraries that offer something similar. I am showing you Scikit Optimize. So go ahead and install the Scikit Optimize library. And once it's done, let's go down. Okay, there you go. And from Scikit Optimize, I am going to import GP minimize. Remember, Gaussian process regressor is what we're trying to use. So let's go ahead and do that. And Scikit Optimize also provides the Gaussian process regressor. Previously, we used it from scikit-learn. Now you can use it from Scikit Optimization right there. And it also provides you the matern kernel. And it also provides you with the Gaussian EI. Remember the EI function where we have written it ourselves by calculating the mean and standard deviation and all that kind of stuff. It's all, you don't have to do that. So with this, the code becomes very simple, just a single line of code. After defining your objective function and the bounds, all you need to do is an empty list, start an empty list with initial points and values because we want to capture and print them. Otherwise, you don't need it. The kernel equals to matern, new equals to 2.5. Remember, this is exactly what we have used when we coded everything line by line. And our GP, we are defining as Gaussian process regressor, where kernel is this, alpha is this. Exactly the same as what we have done with our own hands. Now using someone else's library. Now perform the surrogate optimization, and we are using the GP minimize. We are providing the objective function as the input. We are providing the bounds as input. What acquisition function are we going to use? EI, of course, that's what we ended up using previously. You can change this to number of iterations to 50. I just left it to 30 to see what we get. And random state and everything. And let's go ahead and print the function, the x and the cost value. So let's go down and wait for the result. Let's see, there you go. It's printing out. I think it already found like the solution right in the beginning, 4, 5, -6. You know, I mean, this is not a complex problem, so it should be fine. It should be pretty fast. So of course, we know the answer is 4, 5, and -6, and that's what we got. Cost function is 0, so that's like the best, right? So we want to minimize, and obviously it's minimal at 0. Okay, so that is an easy example. Now let's actually look at a slightly more complex example. Typically, when we talk about a complex example, especially for optimization or evaluation of algorithms, it's common to look at Rosenbrock function, which is basically, it's a function of x and y, and a minus x whole squared plus b times y minus x squared whole squared. Yeah, where usually a and b are constants. Usually they are set to 1 and 100. So let's do the same. And where do you have a global minimum in this function? You have it at x equals to a and y equal to a squared. So one answer could be 1 and 1, right? When x equals to 1, y equals to 1. That would be one answer. So if you set the limits to -5 to 5, -5 to 5 for x and y, you will end up with 1 and 1 answer, depending on your initial position. The other solution could be 2 and 4. So to check if you get 2 and 4, you can change the bounds. Oh, I should have put b right there. I literally finished writing this. Okay, change the bounds to this. Okay, so I'm using exactly the same library as earlier, except I'm changing the function, objective function to Rosenberg function. And let's actually change the bounds here. First, let's start with -5 and 5 and see what we get. I think we'll get 1, 1 or 2, 4, depending on the starting point. But if we get 1, 1, let's change this to 2 and then see if the solution actually changes. So as you can see, as predicted, it gives you 1 and 1. Let's change this to 2 because now the solution cannot be 1 and 1. Obviously, it's beyond the bounds there. So let's see what solution it gives us. Now it's actually thinking, right? So it's going from 2 and 5, and I hope it doesn't just tell me that it's 2 and 5 because the answer should be 2 and 2 squared, which is 4, right? So it should be 2 and 4. So let's go down. So it is going through multiple iterations. Yeah, the best position is 2 and 4, and the cost, global cost, is 1. So go ahead and experiment with this. You plug in your own values here, but the whole point of this tutorial is to make sure you understand what surrogate optimization is and what's going on when you run these optimization algorithms from, for example, a scikit optimization library or whatever off-the-shelf library that you have. So I hope you find this tutorial to be useful, and please do not forget to hit the subscribe button, and let's meet again in the next tutorial. Thank you very much.